Okay. So, stoichiometry. The dimensional analysis. So solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. What mass of gaseous carbon dioxide can be absorbed by 1 kilogram of lithium hydroxide? Before I start this problem, what do I need before I can do any stoichiometry problem? Before I even have that. We need formulas. What else do we need to do with our formulas? Write a balanced equation. So we're going to start by writing a balanced equation. It's on page 15 in the part that's stoichiometry. So find that third section.
It's like 3 pages from the back.
Yeah, it's pretty far back. You're getting close. So if you find 15 in that section, it's exercise 15. There you go. All right. So what was the first reactant it gave us? Lithium hydroxide. What's the formula of lithium hydroxide going to be? Okay. Plus, it would have balanced correctly with sodium hydroxide, but your masses would have been wrong. Lithium hydroxide plus, what's our other reactant? Carbon dioxide, which is? Alright. First product is? Lithium carbonate. What's the formula for lithium carbonate going to be? Just LiCO3? What charge does carbonate come with? 2. So this is going to be Li2CO3 plus what? H2O. Okay, so we got a balance. We need 2 lithiums. Reasonable plan. Is there anything else? No. That balances us. Alright, so then what information does it give us? 1 kilogram of lithium hydroxide. Do we really want to do stoichiometry in kilograms? No. How many grams are in a kilogram? 1,000. So we have 1,000 grams of LiOH. Okay. So, if we're starting with grams of LiOH on top, we need grams of LiOH on bottom, and what are we going to? Moles. You are not in moles, get there. There's like 3 exceptions the entire year. Alright. So what do we need to know about lithium hydroxide to go to moles? Molar mass. Somebody get us our molar mass of lithium hydroxide. 6.941 plus 16 for all intents and purposes.
Right.
So 23.95. Alright. So we're at moles of lithium hydroxide, so we know moles of lithium hydroxide also has to go on the bottom. Where can we go once we know moles of one substance? Use our mole ratio. Where do we get our mole ratio? From a balanced equation. So what other moles are we looking for? So 2 moles of lithium hydroxide. What's going on top? What are we trying to get to? Carbon dioxide. So 1 mole CO2. Okay. And so we've got 1 mole of CO2 on top. We also need moles of CO2 on bottom. And then we need our molar mass on top, which is what? 44.01 grams CO2. It is entirely possible you have the molar mass of carbon dioxide memorized by the end of the year because it shows up a lot. Alright. So, multiply across the top, divide by what's underneath, we should end up with our 920 grams. If you do the math and do not get there, talk to me about it. So that is a basic gram-to-gram stoichiometry problem. What would change about this if we were given moles? We would skip the first step. We would just start at moles, use our mole ratio. What would change if we were given grams but we're trying to get 2 moles? You just cut off the last step. Make sure you do not first change moles to, if you're given moles, use moles. Do not try and change moles back to grams. Because then you have to change it back to moles again. That's just silly. Try to avoid going to grams when you don't have to. So pay close attention to what you need. Otherwise, that doesn't change things. All right. And we'll deal with that one later. All right, let's look at the pictures. Because one thing, I say the newly redesigned AP test, this redesign has been in place for about 5 years now, but it's still new to me. They like doing graphical questions. I don't know why, but pictures of the particulate form, super popular. So let's look at this one real quick. So if we examine the particle views, explain the differences between the two situations with regard to what is or is not reacting and the total yield of ammonia. So in situation 1, does everything react? Yes. So do we have a limiting reactant? No. In situation 2, does everything react?
No.
What's our limiting reactant? Hydrogen gas. Because what is a limiting reactant? What we run out of. We've got nitrogen left over, so in this case, H2 is limiting, N2 is in excess. We've got too much. We couldn't use all of it. All right, so limiting reactants, if you're lucky, they give you, the nice thing with the picture ones is the picture ones are pretty straightforward. You count, and it's either there or it's not. All right, when we're having to do stoichiometry with those, what was the big change when we're doing stoichiometry and worrying about limiting reactants? How many times do we have to do math? As many times that are given. It's usually twice. I've not really seen a situation where they're mean and give you 3 different things you've got to decide between. All right. And by the way, if you just desperately dislike dimensional analysis, they've got this weird alternative method. I don't really get it. They use like a mole table, and if you want to try it, but make sure it's clearly labeled. So nitrogen gas can be, this is exercise 18. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. The other products are solid copper and water vapor. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, what's the limiting reactant? And how many grams of N2 will be formed? So remember, the other name for limiting reactant is limiting reagent. They mean the same thing, but in case it says reagent and things, don't freak out. So it's a stoichiometry problem. So what do I need first? I need the formulas and then the balanced equation. All right. So our first reactant is what? I've got one. It's ammonia because this nitrogen gas can be prepared. Watch out for those things. So ammonia is NH3 plus copper 2 oxide. So what's the formula for copper 2 oxide? CuO. Because it's not. That would be carbon monoxide, by the way. All right. And the products are what? Nitrogen gas, which is just N, N2, plus solid copper, so just Cu, and, all right. So, what do we need? To where? 2 in front of the NH3, which will then give us 6 H's, which means we need how many H2O's? 3, which means we need 3 in front of copper 2 oxide, which means we also need 3 in front of copper. All right? So then, it's not really any more complicated. You just have to do the same thing twice. So, first one, we've got our 18.1 grams of ammonia. What's our next step? Use our molar mass. What's our molar mass for ammonia? Try 17.03 or 17.04, depending on how you're rounding nitrogen. But it's definitely 0.0 something. All right, grams of NH3. Once we're in moles, then we use our mole ratio. So how many moles of NH3 are in my balanced equation? And we're trying to get to what? Grams of nitrogen. So let's go ahead and go to moles of nitrogen, which is 1. And we're going to go ahead and go to grams. You don't necessarily have to go to grams. You can stop at moles and then just convert your final answer to grams, but I just find it easier to add the extra step in advance. All right, and so this is 1 mole of N2 has a mass of what? (0.02 grams N2), and then you do the same thing over again with our copper. Use your molar mass of copper. I'm going to keep going. Somebody can get me the molar mass of copper 2 oxide in a second. All right, balanced equation, how many copper oxides do we have? 3. We're still going to nitrogen. And then 1 mole N2 is still 28.02 grams N2. So what was our molar mass for copper 2 oxides? 79.55. Okay. All right, if you're on that half of the room, do the top one. If you're on this half of the room, do the bottom one. All right, anybody got either of them? For the top? Okay. Okay. Anybody got the bottom one? So, how much nitrogen can we actually make? 10.59. So if I've only got enough copper oxide to make that, it doesn't matter that I have extra ammonia. And then that makes copper oxide our limiting reactant. It's what we're going to run out of. Remember the sandwich analogy. If you've only got enough bread for 10 sandwiches, it doesn't matter if you've got 20 pounds of lunch meat. You're going to be done with sandwiches after you make 10. All right.
We ran out of bread on the softball class while we were in the late game, so we just started wrapping things in lettuce.
Well, yeah. I mean, there are alternatives, but it's not exactly something you would call a sandwich.
It was so bad.
All right. So, theoretical versus actual yield and percent yield. For those of us who have forgotten how this works, it's up here at the top of page 19. Which one can we get from stoichiometry? Theoretical. Theoretically is what we should make in a perfect world. But we don't. There are some reactions that will get very, very close. Like there are reactions where 99% yield pretty common. You got to have a lot of excess of something, but you can do it. There are some yields where you're doing really well to get 30. That it's entirely dependent on what you're doing. A big chemical engineering thing a lot of times is how to get a better percent yield so you're not wasting a bunch of stuff. Or at very least, how to retrieve the stuff that you're not using and use it for the next time. But yeah, that's going to be your life. It's not a bad thing. I mean, the part of chemical engineering I'm kind of interested in, if I was going to do that, is something's gone horrifyingly wrong with this procedure. How do I fix it?
That's exactly what I like.
Like we had a thing we had One thing that actually happened at Dow one time is they made a minor change in how they were doing a reaction and managed to geyser an entire reaction vat. And we're talking like probably at least hundreds of gallons of whatever it was raining down over people's cars in the parking lot. Turned out somebody decided it would be better to switch from using chunks of zinc to powdered zinc. What happens when you go from big pieces to small pieces? More surface area, which means reaction does what? More efficient and more violent. So it's going to happen way, way faster. So if it's something that, say, generates heat, all of a sudden it's going to go from heating kind of slowly to heating very, very quickly. And if you don't adjust yourself, yeah. Something has gone, and yeah, the guy, one of the guys at Dow who used to be in charge of figure out what's gone horribly, horribly, horribly wrong was actually a TLU alum, and he was visiting and told the story, and we had to try and figure out what had gone horribly, horribly wrong. All right, so the other fun thing is chemical engineering is figuring out when it's worth the money to make the improvement, because there are things where a $500 solution is really, really good. There are things where a 50-cent solution is too expensive because it'll cut into your profit margins because you're not making much. Chemi is fun times. All right. Yeah. There's a lot of really cool stuff going on in that. All right, so methanol, also called methyl alcohol, is the simplest possible alcohol. This, by the way, is the one that will make people go blind. It's used as a fuel in race cars and as a potential replacement for gasoline. Methanol, however, really, really violently combustible and vaporizes a lot more easily, so not really a good replacement for gasoline. Also, way more water soluble, which can cause its own problems. Alright, so methanol can be manufactured by a combination of gaseous carbon monoxide and hydrogen. Suppose that we have 68.5 kilograms of carbon monoxide. It's reacted with 8.6 kilograms of hydrogen gas. Calculate theoretical yield of methanol. And if we actually produced that, what would be our percent yield? So, first of all, let's talk through this. What would our steps be here? What was the first thing we'd have to do? Balanced equation. Okay. Next thing, what would we have to do? Find the limiting reactant. So we got to do stoichiometry twice. What would our next step be?
Find how much is actually produced.
Well, before we find out how much is actually produced, we've got to find our theoretical. So whatever our lower number is will be our theoretical yield. And so then step 4 would be percent yield, which equals, anyone remember?
Actually, your yield over theoretical yield.
And remember, where should you always be getting your actual yield?
Oh, sorry.
From the problem, unless the only exception to that is they give you find your theoretical yield and they give you your percent yield and you work backwards from there. You cannot find an actual yield from stoichiometry. It doesn't work. All right, so at this point, if you want to work through this one and get me to check it, you can. But otherwise, I'm going to let you go on your own. So, at least one person from your group needs to go back. Find your copper. Weigh your copper. Y'all's copper is actually very pretty, or at least it was on Friday. So yeah, find your copper, weigh your copper, and then either finish up your lab or work on your quest, or both, depending on what we've got time for.